Yeah. So for simple linear regression, I want to cover a couple of more prior choices that you can make. So the one that we did so far is weakly informative prior, right? Like we just put very like gamma 1 for those sigmas, or like the other standard deviations, and then for the means we're putting very big prior because we center it to be 0 the regression coefficient and give it a really large standard deviation. But there are other ways you can do priors. We're going to cover 2 of them. The first one is subjective prior, in a sense that you can actually incorporate your belief into the Bayesian inference. But before we get there, we have to do what we call standardization. You probably have heard this term before. And standardization, when you're doing simple linear regression, you have one continuous response, and for now you have one continuous predictor. What you do is you standardize them. That is, subtracting each observation by its mean and then divided by its standard deviation. Right? So standardizing can help put different variables on a similar scale. What this is going to turn out to be is you can use, in R, you can just use the scale function and it will scale to the standardized version that you want. But of course, looking at equation 20, I think you probably also know how to write it out if you just need to write a function. But scale function does that for you. But I do want to show you that after you standardize the data, the general shape wouldn't change, the relationship between them. Okay, what you do is simply just put them on the same scale. And what we mean by same scale, so if you look at the right model, like the plot on the right, you can see that the log income on the x-axis, I guess, ranges from -4 to +2, right? And whereas the log expenditure standardized is from -5 to 2.5. So the data is definitely like skewed in some way. But typically, once you do standardization, we know that, well, if you have a normally distributed data, then you will know that like majority of the points going to be between -2 to +2, all that kind of stuff. So you're able to put them on the same scale, okay? And that's what we do by standardization. The reason why we do standardization to do subjective prior is because later it's much easier for us to interpret the correlation, the regression coefficients. So before we get to the details of how to specify the prior, and I do want to ask you to think about, once we do standardization, let's say X, so X is the log income, okay? And then Y is the log expenditure. And now when I put the star on those parameters or random variables, we're talking about the standardized version of it. So what do you think Xi star equals to -2 mean? And what does Yi star equal to 1 mean? Again, once you do standardization, it represents the number of standard deviations that the value falls below or above the mean. So once we do standardization, what do you think this 2 represents? So I'm just going to write Xi is log income, and Yi is log expenditure. So maybe talk with your neighbors to make sure that you have similar understanding of what does it mean to have like -2 for Xi star and +1 for Yi star. All right, so what do you think Xi star equals to -2 mean? And what about Yi star is 1? Yeah, maybe you can pick one to talk about. Standardized value. Standardized X and standardized Y. Zach?
I did the math in my head, so I don't even remember if it's right, but it's 0.025% probability of this observation occurring like posterior from -2 from the mean.
What was that again? Sorry, I missed
between -1 and 1 is 84, right? So then like anything that's -2 below standardized would be 50 plus 42 plus 5.
Yeah, okay. Right, so I think Zach is referring to, okay, so we're gonna come back to that, whether we should think in that way or not. But what Zach is referring to is if you have a normal, I guess you're talking about like a normally distributed data, then we have this. So this is the mean. This is within one standard deviation. And the normal distribution will have 68% roughly 68% within the first, within one standard deviation. So that's mu. Yeah, that's mu minus sigma and mu plus sigma. And then if you move forward, that you have mu minus 2 sigma, mu plus 2 sigma, then all of this will be about 95%. Okay? If you do 3 sigma, it's going to be, I think, 99.7. Yeah. So I think that's what you're referring to, right? Yeah. So okay, so I'm just gonna ask, should we think about the normal model at all in this case, or not really?
Don't we know that it's not normally distributed, and isn't that why we did the law thing?
Oh yeah, there's that. Right. Okay. Yeah, that's a good point. So I guess even if after we take the log, do you think we should be thinking about the normal model per se? What we're doing the normal model in the first place in this case? So we learned about normal model early on in the semester, because say when you have continuous outcome and you believe that, like say all of the observations follow say the same normal distribution, for example, then you're saying that, well, it's gonna roughly looking like a normal. But when you're doing regression again, so I'm just gonna spend the time, I guess, talking about this again, that when we're talking about normal regression or like simple linear regression that we're talking about right now, we're saying that the observation independently follows normal distribution with its own mean, which is expressed by this setup, right? And then with sigma. And remember the plot that we used to do last time, that the mean, the one that we're trying to fit, the line that we're fitting, is really just about the average. And that's the expectation, right? So when you have different values of x, so let's say this is x, this is y. So the line that you're fitting, the lines go through the mean. Okay? And last time we had this, I think actually Julie after class asked me about how we can express the model most correctly. So the sigma here is talking about, well, around the mean for each observation, how variable your observation is actually behaving. Okay? So that's why linear regression is really thinking about models like this. Sorry about my terrible drawing here, but I'm trying to draw just vertical. Yeah, it's really bad, sorry. Yeah, so anyway, you get the point that this is the mean, and the sigma and the normal model we're talking about is capturing the variability once we fix the mean. Okay? It's not talking about like all of the data together follow a normal distribution. Okay? So I wouldn't say that we have to go that far to come to talk about this. But yes, this is a good, I guess, refresher about the normal distribution in the first place. And then if you standardize the data, and we know that, so I should also mention standardization can happen to any numerical data or numerical variable. It does not have to be a normal. If it's a normal, it's going to follow the rule that we talked about. But if it's not, the standardized value still tells you, like say, how many standard deviations away this observation is from its mean. Okay? So when you have an observation of x star to be -2, you can say that this observation is 2 standard deviation below the average log income. That's what it is. Okay? And if you have yi star to be 1, that is saying that this observation, the outcome, which is the log expenditure variable, it is 1 standard deviation above the expected value of that. Okay? So that's what those values are about. And the reason why I asked you for this is, well, after you do the standardization, you can just add the star symbol to all of the parameters. Sorry, not parameters, the random variables. In our case, add it to the mean because xi is being standardized, and then the yi is being standardized as well. So you can rewrite the model in this way. So yi now star is the standardized log income. Xi star is the standardized, log expenditure and log income, respectively. The intercept now becomes something different now. So intercept, even though we still have the general write-up, but beta 0 now is the expected standardized log expenditure for a particular consumer unit that has the average log income, because now for that observation, the xi star is 0. So you see, it's a little bit more involved, but we have to get this clear before we move on to the actual modeling. And then similarly, when you're working with slope, beta 1, again, it's the change in the expected standardized log expenditure when the standardized log income increases by 1 unit. Because not everything works on different scales, but standardization altogether can put us on the same scale for all of the different variables that you work with. And I should also mention the really main reason why we do standardization is because once you do standardization for a simple linear regression, the slope, beta 1, becomes the correlation. Okay, you might have seen this before, so we won't derive it in class, but what this beta 1, the slope, means is the correlation between the standardized predictor and the standardized outcome. So that gives us a lot of power, because if I have strong opinion about the correlation between the two, I can play with my beta 1, right? Earlier, we didn't do standardization, we're just on the raw data or the original scale, and we probably have no idea about beta 0 and beta 1 should be, especially beta 1. You don't know what the slope would be. But now, once you do standardization, slope, beta 1, is the same as the correlation between the standardized standardized predictor and standardized observation, then you can actually directly work with beta 1 if you want to give it a particular prior. Like if I have very strong opinion that I think the correlation is high, positively high, then I wouldn't put the mean to be 0, right? I might put some different normal distribution for that. So that's the main reason why we want to do standardization. So when we come back on Thursday, we're gonna look at how to express that model, and then we're also gonna rely on DEX to do the actual MCMC estimation. All right, so end here today.